Hello Year 11, here are the answers to your 5 a day. Let me know if you have any questions about those. So today we are starting on a new chapter on complex numbers, and today's lesson is looking at starting to build the complex numbers and how to perform arithmetic with imaginary numbers, which you may have heard of before, you may not have heard of before, but we're going to be getting into the interesting world of numbers that when you square them, they give you negative answers. So, you know that some quadratic equations cannot be solved or do not have real solutions, might be how you put it. And imaginary and complex numbers are going to allow us to solve these. And just a reminder of why some of these can't be solved. So this is our quadratic formula, and this part here is known as the discriminant, the b squared minus 4ac. And it tells us how many solutions a quadratic equation has. So when it is greater than 0, we know that it has 2 real roots or solutions. When the discriminant is equal to 0, we know that it has 1 real root or solution. And when it's less than 0, we know it has no real roots. This is because up until today, we cannot square root a negative number. But we can introduce something called the imaginary number. We're going to call it I. The definition of I is that I squared is equal to -1. This will enable us to solve equations where our discriminant is less than 0. We can combine our imaginary number with real numbers to create a group of numbers called complex numbers. This is an example of a complex number, which we would read 5 plus 2i. Complex numbers can be added, subtracted, multiplied and divided in the same way that we would with an algebraic expression. So let's have a look at just formalising this slightly. So a complex number is an expression of the form a plus bi where a and b are real numbers. The set of complex numbers is denoted by the double C. When you are writing this, draw a C, put a line on it. And this is how we can write it in set notation. We often use Z to represent a complex number. And so if Z is a complex number, then it is equal to a plus bi for some a and b that are real numbers. If the a part is equal to 0, then Z is equal to bi, and it's called an imaginary number. If the b is equal to 0, then Z is just equal to a, and it's a real number. The real numbers and the imaginary numbers are subsets of the complex numbers. And you might remember this diagram, which we looked at right at the beginning of the year. We were looking at different types of number. We can now add a new set that encompasses all of the others that we've looked at so far. And that's our complex numbers around the outside here. So for a complex number, Z equals a plus bi, we define the real part of Z to be a and the imaginary part of Z to be b. For example, in 5 plus 2i, the real part is equal to 5 and the imaginary part is equal to 2. Note that both of these are real numbers. The imaginary part is not 2i, it is just 2. Two complex numbers are said to be equal if both their real parts and imaginary parts are equal. So if a plus bi equals c plus di, this can only be true if and only if a is equal to c and b is equal to d. So here, if we're told that these two complex numbers are equal to each other, then I know that the real part must be equal to the real part, and the imaginary part must be equal to the imaginary part. Then I can, well, the b is already solved for. I can solve for a to get a equals 2 and b equals -3. Pause the video now while you have a go at questions 1 and 2 from exercise 16a. And here are your answers. So we can simplify complex expressions. And here's some examples. Here I have two complex numbers and I'm adding them together. All I need to do is collect up the real parts and collect up the imaginary parts. So 2 plus 7 is 9, 5 plus 3 equals 8i. Here I just need to be careful because I'm subtracting here. Now you don't have to do this step, but just be careful that you know that this is subtract 5 and add 11i, and then collect up your like terms again. When we're multiplying, just the same as multiplying out a bracket as normal. Pause the video now while you have a go at question 3. And here is your answers. Here are your answers. Okay, so we can simplify surds as well. The square root of -36 rewritten in terms of I. So this means the positive square root because it doesn't have a sign in front of it. So we can start by splitting up the -36 into 36 and -1. Then we can simplify each part. We know that the square root of 36 is 6 and the square root of -1 is I. Let's have a look at a second example. So we've got the square root of -28. Start by rewriting into the positive and the negative part. Now 28, hopefully you can notice that we can split that up further because 4, which is a square number, is a factor of 28. So then I can simplify some of these square roots, and we tend to write it with the I in front of the square root symbol just so it doesn't get lost underneath it. So some other simplifications we can do. I to the power of various things. So let's have a look at I to the power of 3. I can rewrite that as I squared times I. I squared is -1. So that's like saying -1 times I, which I can just write as -I. I to the power of 4. I can rewrite that as I squared times I squared, which is -1 times -1, which is 1. When I have a bracket raised to a power, remember everything in that bracket must be raised to the power. So that's 2 to the power of 5 times I to the power of 5. I to the power of 5, I can rewrite as I squared times I squared times I. I can evaluate the 2 to the power of 5 and the I squareds, and then simplify. So now you can have a go at questions 4 and 5, and while you're doing this, have a think about, can you make any generalizations about I to the power of A, where A is the natural numbers? The more you do this, the quicker you'll get at doing it. It's a bit like times tables. You'll start just memorizing what each of them are. So your answers to question 4 and 5 are here, and you should have noticed for this that if I is to the power of a multiple of 4, then it gives you 1. I is to the power of a multiple of 4 plus 1, then we get I, and so on. So even powers always give us 1 or negative 1, and odd powers always give us I or negative I. Let me know if you have any questions. Thank you.